Section 5.1, Approximating Areas. Before we start talking about how to approximate the area under a curve, which is the second problem that helped motivate the development of calculus, we have to talk about a notation that lets us summarize very long addition. And this notation is referred to as either sigma or summation notation. And as stated before, this is used to express long sums of values in a more compact form. Below, we see an example of sigma notation. The symbol that looks like an E is the capital letter sigma, which is from the Greek alphabet. AI describes the terms that we are adding together. Usually it'll be some sort of equation. I is called the index, and each term is evaluated based on the AI rule. Then we sum all of those values, and we begin with the value of I equals 1, and we end with the value of when I equals n. For some examples of how sigma notation works, we're going to find the sum from I equals 1 to 5 of I squared plus 2. Here, the I squared plus 2 is the AI, and that will represent basically the pattern that our terms will follow. Our index is I, and based on the bounds of our summation, we're going to start with I equals 1, and we're going to increase I until we get to 5. So to calculate our sum, we're going to take I equals 1 and plug it into our a sub I, and we get that the first term is I squared plus 2. Then we'll add the result for when we plug I equals 2 into our AI formula, and we get that the second term is 2 squared plus 2. And we're going to continue this for I equals 3, I equals 4, and because our upper bound in the sigma notation is 5, we stop at I equals 5. And when we plug in I equals 3, 4, and 5, we get that the third, fourth, and fifth term are 3 squared plus 2, 4 squared plus 2, and 5 squared plus 2. Now that we've expanded our sigma notation, we can begin to evaluate, and we get that the first term is 3, the second is 6, the third term is 11, the fourth term is 18, and the fifth term is 27. And if we add those all together, we get that our sum equals 65. Even though the letter I is most commonly used to represent the index in summation notation, I doesn't always have to be used. In our next example, we'll use the letter J for the index. In the definition, also note how we started off with the index being equal to 1. Most definitions do tend to start with I equals 1. Some books may use I equals 0, but the lower bound of the index can be whatever number we want it to be. In this example, we're going to start off with our index being equal to 4, and we're going to stop when our index is 8. So we'll start off by plugging j equals 4 into our formula 5j minus 1, and we get that the term associated with j equals 4 would be 5 times 4 minus 1. Then for j equals 5, our term would be 5 times 5 minus 1, and we're going to continue doing this for j equals 6, 7, and 8. Now we can proceed to simplify, and when we simplify and add up all our terms together, we get that the sum is 145. Now we're going to rewrite each sum using sigma notation. An exercise like this can be rather difficult since it requires us to recognize patterns. For our sigma notation, let's make our index I, and we're going to start with a lower bound of 1. So our first term is what we'll get if I equals 1. Then the second term will be for when I equals 2. Then 6 would be what we get when I equals 3. 8 would be what we get when I equals 4, and so on. From these first 5 terms, can we identify a pattern that we can use to relate the value of I to the value of the term itself? First thing I notice is all of our terms are even. More specifically, our first term is 2 times 1. Our second term is 2 times 2. 6 is 2 times 3. 8 is 2 times 4. And 10 is 2 times 5. So it appears that for each term, I'm taking my index value of I and multiplying it by 2. So my AI is going to be 2i. But what will be my upper bound? The ellipses, which are the 3 dots in between the plus sign, indicate that this pattern continues. So to obtain every term, I'm taking 2 and multiplying to the index. How do we obtain 124? If our pattern continues, we would multiply something by 2 to obtain 124, and that something would be 62. So 124 from our pattern would correspond to when I equals 62. And since that is the last term, then our upper bound for our summation would be 62. So our sum would equal the sum from I equals 1 to 62 of 2i. For our next sum, we're adding 1, 4, 9, 16, and we're continuing down to 225. Just like before, to write it in summation notation, we'll start off with our index being I, and we'll set the lower bound to 1. So 1 would be the term corresponding to I equals 1, 4 would correspond to when I equals 2, 9 would come about from when I equals 3, 16 would come from when I is set equal to 4. Can we figure out a pattern of 1, 4, 9, and 16? This is where it's a little tricky. If we're familiar with perfect squares, we can identify that 1 is 1 squared, 4 is 2 squared, 9 is 3 squared, 16 is 4 squared. So it appears that the pattern is we're taking the value of I and we're squaring it. So our AI seems to be I squared. If this pattern continues, what number squared would give us 225? Well, 15 squared is 225. So 225 would come from when I equals 15. So our upper bound in our summation is 15. So our sum in sigma notation is the sum from I equals 1 to 15 of I squared. Note that writing sums in sigma notation can be a little bit challenging because of the pattern recognition. Sometimes it requires a little bit of playing around, and you may not always get it in the first try. If you're not sure that your AI is correct, you can always expand the sum just to check to make sure you are getting the proper terms. Now we're going to discuss some properties of sigma notation along with rules that we can use to quickly find the sum of sigma notation in certain circumstances. First, we'll talk about the properties. For these properties, we're going to let a1 through an and b1 through bn represent two sequences of terms, and we're going to let c be a constant. The following properties hold for all positive integers n and for integers m where 1 is less than or equal to m, less than or equal to n. For the first property, the sum from I equals 1 of c times ai equals c times the sum from I equals 1 to n of ai. In other words, we can kick constant multipliers out of our summations. The reason why this is true is if we expand the sum of the c times ai, that'd be c times a1 plus c times a2 plus, and we'll keep going to c times an. Since we see that c is a common factor of each term, we can factor that out of the sum. And when we factor out the c, we get c times the sum of a1, a2, all the way down to an, which the a1 plus a2 plus all the way down to an, we can summarize with the sigma notation. So this first property comes from us being able to factor out common factors from a sum. Our next property is that the sum from I equals 1 to n of ai plus bi equals the sum from I equals 1 to n of ai plus the sum from I equals 1 to n of bi. So the sum of two sequences equals the sum of the two summations. This is a result of the commutative and associative property of addition. If we expand the summation on the left-hand side, we get a1 plus b1 plus a2 plus b2 plus all the way down to an plus bn. Because addition is commutative, meaning the order of the terms does not matter in addition, we can rearrange the terms so all the a's are together and all the b's are together. And we get a1 plus a2 plus all the way down to an plus b1 plus b2 plus all the way down to bn. Because of the associative property, we can group the an's together, we can group the b's together. The sum of the a's would be the sum from I equals 1 to n of ai, while the sum of the b's would be the sum from I equals 1 to n of bi. Now, similar to addition, we do also have the same property for subtraction. If we have the sum from I equals 1 to n of ai minus bi, that equals the sum from I equals 1 to n of ai minus the sum from I equals 1 to n of bi. So the summation of the difference of two sequences equals the difference of the summation of those sequences. This comes about by the fact that all subtraction is addition with an opposite. So we can rewrite the ai minus bi as ai plus negative bi, and then apply a combination of the first two properties. And we'll leave that as an exercise for you to finish, that applying the sum rule first, followed by the constant multiplier, we do get the right-hand side. As for our last property, the sum from I equals 1 to n of ai equals the sum from I equals 1 to m plus the sum from I equals m plus 1 to n of ai. Remember that from the conditions, m is between 1 and n. So if we expand out our sum, somewhere between I equals 1 and I equals n would be I equals m. So the first part of our left-hand side would expand to the sum of a1 plus all the way down to am. After am, we would have the m plus 1 term, am plus 1, and this would continue all the way down to n. Thanks to the associative property, we can group the first m terms together, which would give us the first sum on the right-hand side, and we can group the last m terms together to obtain the second sum on the right-hand side. Now we're going to go over some summation rules that can help us evaluate very long sums. The first one is the summation from I equals 1 to n of a constant c equals c times n. The reason why this is true is the left-hand side is us adding c to itself n times. Well, adding a number to itself n times just means we're multiplying that number by n. So it comes as a direct result of the definition of multiplication. The next three properties involve adding powers of I together. The derivation of these is not very intuitive, but you can find them easily online. The first, the sum from I equals 1 to n equals n times n plus 1 all over 2. In other words, if I add together the first n positive integers, I get the sum of n times n plus 1 all over 2. The next property has us adding together the first n perfect squares, this being the sum from I equals 1 to n of I squared. This will equal n times n plus 1 times 2n plus 1 all over 6. And lastly, the sum of the first n perfect cubes. This will be the sum from I equals 1 to n of I cubed, and this will equal n squared times n plus 1 squared all over 4. We'll see how these can help us with very long sums in the next example. Now we're going to compute the following sums. We'll start with the sum from I equals 1 to 100 of 3i cubed minus I squared plus 2. We could write out the sum term by term, just like what we did in previous examples. However, since I ranges from 1 to 100, we would be writing 100 terms, and we would have to add all 100 terms together. Instead, we can use the properties that we've discussed in the prior slides. One thing to note is I do have summation rules for I cubed, I squared, and 2. So I want to apply the sum and difference properties and the constant multiplier properties just like what we did for problems that involve limits, derivatives, or antiderivatives. And we get the sum from I equals 1 to 100 of 3i cubed minus the sum from I equals 1 to 100 times I squared plus the sum from I equals 1 to 100 of 2. In the first term, since we have 3i cubed, we can apply the first property we discussed where we can kick the 3 out of the summation. And our first summation becomes 3 times the sum from I equals 1 to 100 of I cubed. Now we can apply the appropriate sum and powers of integers properties that we discussed before. For each sum, n would be 100. For the I cubed, its sum would be 100 squared times 100 plus 1 squared all over 4. For the I squared, that would be 100 times 100 plus 1 times 2 times 100 plus 1 all over 6. And as for the sum of 2, that would be 2 times 100. Now we can punch this into the calculator to finish evaluating, and we get 76,169,350 as the sum of I equals 1 to 100 of 3i cubed minus I squared plus 2. Now we're going to find the sum from I equals 1 to 50 of I plus 1 squared. If we look at the list of summations we can find the sum of, we do have a rule for I squared, but not I plus 1 squared. So what we should try to do is expand out the I plus 1 squared and see if we can break it apart using our other properties. I plus 1 squared is equal to I squared plus 2i plus 1. Now our summation looks very similar to what we did in the last problem. So if we apply the sum and difference rules and that constant multiplier rule that we saw in the previous slide, we can break our summation down to I equals 1 to 50 of I squared plus 2 times the sum from I equals 1 to 50 of I plus the sum from I equals 1 to 50 of 1. Now we can apply our formulas. For all three, n would be 50. Our first sum would be 50 times 50 plus 1 times 2 times 50 plus 1 all over 6. Our second sum would be 50 times 50 plus 1 over 2. And our last sum is 1 times 50. Now we can punch these values into our calculator, and we get that our sum is 45,525. Now we're going to discuss approximating area, which is the second problem that motivated the development of calculus. Suppose we want to find the area of the shaded region that we see in blue on the right. The problem with trying to find this area is we can't break this shape up into basic shapes that we understand how to find the area of. Basic shapes are shapes like circles, rectangles, triangles, trapezoids, and so on and so forth. Shapes that we have a formula for calculating the area. But because of the curve from the graph of f of x, I can't break it down into circles or squares or rectangles or things that I know how to calculate the area of. So right now, the best we can do is approximate the area. And the way we're going to approximate the area is by trying to create rectangles that fit within our region. And through these rectangles, we can find their areas because we know the formula, add them together, and that's going to give us an approximate value of the area of this region. Before we discuss popular methods that are used to construct the rectangles to approximate the area, we're going to talk about partitions. A set of points, p which equals xi for I equals 0, 1, 2, all the way down to n, with a being equal to x0, which will be smaller than x1, which will be smaller than x2, and so on and so forth until we get to xn, which will equal b, which divides the interval ab into subintervals of the form x0 to x1, x1 to x2, all the way down to xn minus 1 to xn, is called a partition of the interval ab. We can think of partitions as us breaking our interval into different pieces. For example, the interval 0, 1, 1 to 1.5, and 1.5 to 3 is a partition of the interval 0 to 3. Notice how where one interval ends, the other picks up, and if we put all three intervals back together, we do get the entire interval 0 to 3. Now, nothing in the definition of partition says these intervals have to be of even width. However, for our methods that we're going to develop to approximate the area, we are going to want our partitions to consist of intervals of the same length. If the subintervals all have the same width, then the set of points form a regular partition of the interval AB. For example, 0, 1, 1, 2, and 2, 3 do make a partition of 0, 3, but notice how they all have a width of 1. Therefore, it's not just a partition of 0, 3, it's a regular partition of 0, 3. Two popular methods for constructing our rectangles are going to be referred to as the left and right endpoint approximation. We're going to let x0, x1, x1, x2, all the way down to xn minus 1, xn, be a regular partition of the interval AB. Each interval will have a width which we'll call delta x, which will be b minus a over n, and we're going to assume f of x is a continuous function. What these two methods are going to do is they're going to allow us to approximate the area that is located between the curve of the graph of our function f of x and the x-axis over the interval a to b. As for the left endpoint approximation, we're going to let ln denote the left n approximation using n intervals in our partition. Each interval is going to be used to create a rectangle. So n not only represents the number of intervals in our partition, it also represents the number of rectangles we are forming in this approximation. Each interval is going to serve as the base of our rectangle. The height of our rectangle is going to be generated by taking the left endpoint of each interval in our notation and plugging it directly into our function. So for example, the area of our first rectangle for the interval x0 to x1 would be f of x0 times delta x. The f of x0 being the height of the rectangle by taking the left endpoint of our partition, plugging it into our function, the delta x coming from the width of our rectangle, which is the width of our interval. Our second rectangle would have an area of f of x1 times delta x, f of x1 being the height of our rectangle, coming from taking the left endpoint of the interval x1 to x2, plugging it into our function, delta x coming from the width of the interval. And we're going to continue doing this until we get to the last partition, which would generate a rectangle with an area of f of xn minus 1 times delta x. Using the summation notation, ln would equal the sum from I equals 1 to n of f of x sub I minus 1 times delta x. The x sub I minus 1 represents the left endpoint of each subinterval. As for the right endpoint approximation, it's very similar to the idea of left endpoint approximation, where the height of each rectangle is going to be determined by plugging values into our function. The difference is we're going to be plugging in the right endpoint of each interval from our partition. So for example, the area of our first rectangle would be f of x sub 1 times delta x, the f of x sub 1 representing the height of the rectangle by plugging in the right endpoint from the interval of x0 to x1. And our second rectangle generated by our second interval in our partition would be f of x sub 2 times delta x, all the way down to the area of our last rectangle, which would have a height of f of x sub n times delta x. Using the summation notation, this would equal to the sum from I equals 1 to n of f of x sub I times delta x. The x sub I would represent the right endpoint of the ith interval in our partition. Very similar to the left endpoint, we're going to use r sub n to represent this right endpoint approximation. N would represent the number of intervals in our regular partition, which would be the same as the number of rectangles we are creating. One important thing to note is if f of x is positive, then the sum of these areas of these rectangles will approximate the area between the graph of our function f of x and the x-axis. We're going to talk later about what happens if our function is negative. Does this left and right end approximation still tell us anything? We'll discuss that later on. We're going to let f of x equal x squared plus 2, and we're going to estimate the area under f of x over the interval 0 to 2 using the following scenarios. First, we're going to use the left endpoints with 4 rectangles. The first thing we should figure out is delta x, which is the width of each rectangle. To find delta x, we'll find the length of our interval, which will be 2 minus 0, and divide that by how many rectangles we want to break the interval up into, which in this case is 4. And we get that our delta x is 1/2. From there, it does help to visualize our partition of our interval 0 to 2. To help us visualize, we'll draw the number line from 0 to 2 to represent our interval. Now we'll figure out the endpoints of each interval. We know each interval is supposed to have a width of 1/2. Starting at 0, if we add 1/2, we would get that the end of our first interval, which would also be the start of our second interval, will be 1/2. Add our delta x again, and we get that our second interval ends with 1, and our third interval begins with 1. Add 1/2 again, and we get 3/2 as the next endpoint for our next 2 intervals. And if we add 1/2 again, we do get 2. If we calculated delta x correctly, we should end at the right endpoint of the interval we're trying to partition. We do have 4 subintervals, 0 to 1/2, 1/2 to 1, 1 to 3/2, and 3/2 to 2. Since we're using the left endpoints to estimate our area, it helps to circle what the left endpoint of each interval would be. The left endpoint of our first interval is 0. In the second interval, it would be 1/2. In the third interval, it would be 1. And the fourth interval, it would be 3/2. So our area would be approximately equal to f of 0 times delta x, which would be the area of our first rectangle, plus f of 1/2 times delta x, the area of our second rectangle, plus f of 1 times delta x, the area of our third rectangle, plus f of 3/2 times delta x, which is the area of our fourth rectangle. Now we will evaluate our function at each of our left endpoints. F of 0 is 2, delta x is 1/2, f of 1/2 is 9/4 times delta x, which is 1/2, f of 1 is 3, and f of 3/2 is 17/4. And again, each of those multiplied by 1/2, which is our delta x. If we punch that into the calculator, and we get that our area is 23/4, and for comparison, that'd be 5.75 as a decimal. Now we're going to approximate the area using the right endpoints with 4 rectangles. Our partition is still going to be the same as before. The only difference is, in each of the subintervals, we're going to use the right endpoint instead of the left. In the first interval, we would use 1/2. For the second interval, we'll use 1. In the third interval, we'll use 3/2. And in the fourth interval, we'll use 2. So the area is going to be approximately equal to f of 1/2 times delta x, plus f of 1 times delta x, plus f of 3/2 times delta x, plus f of 2 times delta x. From there, we can work out the computation, and we get that the area is approximately 31/4, or 7.75. Next, we're going to repeat the previous 2 examples, but this time we're going to use 8 rectangles instead of 4. Just like before, we'll start off by calculating our delta x to figure out how wide each subinterval in our partition should be. That'll be 2 minus 0 over 8, since we want 8 rectangles, which will be 1/4. Now to visualize, we'll draw a number line for the interval 0 to 2, and for each endpoint in our partition, we'll add 1/4 recursively. So starting with 0, add 1/4, we get 1/4, add 1/4 again, we get 1/2, and if we keep going, we get 3/4, 1, 5/4, 3/2, 7/4, and then finally 2 as the other endpoints to our partition. Now for the left endpoint, we would use 0, 1/4, 1/2, 3/4, 1, 5/4, 3/2, and 7/4. So our area would be approximately equal to f of 0 times delta x, plus f of 1/4 times delta x, plus f of 1/2 times delta x, f of 3/4 plus delta x, plus f of 1 times delta x, plus f of 5/4 times delta x, plus f of 3/2 times delta x, f of 7/4 times delta x. Recalling that our delta x is 1/4, and we plug each value into the function and multiply that value by 1/4 and add them all together, we get that the area is approximately equal to 99/16, or 6.1875. Now we'll approximate the area using the right endpoints with the 8 rectangles. We still will use the same partition that we did for the left endpoints with 8 rectangles, but this time we'll use the right endpoints to approximate our area. So our area is going to be approximately equal to f of 1/4 times delta x plus f of 1/2 times delta x plus f of 3/4 times delta x plus f of 1 times delta x plus f of 5/4 times delta x plus f of 3/2 times delta x plus f of 7/4 plus delta x plus f of 2 plus delta x. Using delta equal to 1/4 and plugging each value into our function, multiplying and adding everything together, we get 15/16, which is 7.1875. Notice how changing from 4 rectangles to 8 rectangles made the left and right endpoints approximations closer and closer. We're going to discuss more about the effects of using more rectangles in the next slide. Now we're going to discuss a few more notes on those approximation methods. In general, we can pick any point xi star from the interval x sub I minus 1 to x sub I. So we're not just limited to having to use the left endpoints or the right endpoints, nor does there have to be a systematic way of picking those points. We call the sum from I equals 1 to n of f of xi star times delta x a Riemann sum. The left endpoint approximation and the right endpoint approximations are all examples of Riemann sums. It's just that there we're being more systematic about the points we're using in each partition. One thing that's important to notice, if we take a look at the image on the right, notice how using 8 rectangles versus 32 rectangles, notice how the rectangles seem to fit better when we're using the 32 rectangles versus the 8 rectangles. In general, as n increases, the width of the rectangles do get smaller. Since the width is getting smaller, that means we can better place the rectangles within the region. Just like with pictures, if we can place really, really small pixels within an image, we can get much crisper images. So this is going to cause the approximation of the area that the Riemann sum provides to approach the actual area between f of x and the x-axis. So if A is the area between the graph of f of x and the x-axis, then we have that the actual area is equal to the limit as n approaches infinity of our Riemann sum. We've already discussed that if f of x is non-negative, then the Riemann sum approximates the area between the x-axis and the graph of f of x. This is because the height of each rectangle is based on us evaluating our function at various sample values for our subintervals. Since our function is positive, then we can see from the diagram on the right, the rectangles would have a positive height that we would expect geometrically, creating a positive value, which would represent the area. However, what happens if our function dips below the x-axis? If f of x can be negative, we can still calculate the Riemann sum. However, the Riemann sum will approximate what we're going to call the net signed area. If we look at the figure on the right, this region from 1 to 2 is below the x-axis. The Riemann sum will have us evaluate the function for sample numbers of these subintervals. Now, for each of these values, the function will be negative, which we can interpret as our rectangles having a negative height, which will cause our area to be negative. Now, geometrically, this may not make sense since area should be a positive quantity. And this is why we refer to it as signed area, to allow that possibility of negative values for when our curve dips below the x-axis. As for where the net comes in, if our function is a mixture of positive and negative values over the interval, if A1 is the total area between f of x and the x-axis of the regions where f of x is positive, and A2 is the total area between f of x and the x-axis of the regions where f of x is negative, then the net signed area is A1 minus A2. Now, A1 and A2 are both positive because we are using area in the proper geometric sense. But A1 represents where we're above the curve. We give that type of area a positive sign, whereas the A2 being below the x-axis, we give that a negative sign. And taking a positive value, adding a negative value is the same as subtracting. One thing to note is this net signed area can be a negative quantity. That just means the area below the x-axis was greater than the area above the x-axis. Even though geometrically net signed area may not make sense, it does have some important applications that we will discuss later.